In today's lecture, I'm going to talk about the subdifferential maximum rule. This is another important calculus rules for subdifferentials. In this figure, we see three functions. The first function is f1 of x equals minus x. And this is the graph of the first function. The second function is f2 of x equals 1. And the third function is the identity function f3 of x equals x. Even though f1, f2, and f3 are not differentiable functions, the max of the three functions defined by f of x equals max of f1 of x, f2 of x, f3 of x is a non-differentiable function. As you can see, this is the graph of the max function of the three functions. So a natural question appears as follows. How can we represent the subdifferential of the maximum function f at a point x bar in terms of the subdifferential of fi of x bar for I from 1 to 3. Okay, so in today's lecture, I'm gonna give the answer to this question. So the situation is described as follows. Let fi from Rn to the extended real line for I from 1 to m be convex function. We define the following function. F of x is equal to the max of fi of x, where I runs from 1 to m. We also define the active index set at a point x bar as follows. Given x bar in Rn, we define I of x bar to be the set of all I from 1 to m such that the maximum is attained in the definition of the maximum function. That means fi of x bar is equal to f of x bar. In order to understand the active index set, we're gonna look at this example. Now, in this example, consider the case where x bar is equal to 1. Okay, this is x bar. In this situation, we have the following. f1 of x bar is equal to minus 1 because f1 of x is equal to minus x. f2 of x bar is equal to 1 because the function f2 is the constant function. And f3 of x bar, as you can see here, is 1. Okay. Now, by the definition, f of x bar is the max of minus 1, 1, and 1. So f of x bar is equal to 1. Now, if we look at the set of all indices I, such that fi of x bar is equal to f of x bar in this situation, we see the following. f2 of x bar is equal to 1, and it is equal to f of x bar. And f3 of x bar is also 1. So in this situation, we see that the set of all indices I, such that the maximum is attained, is equal to 2, 3. Okay. Okay. And similarly, in the case where x bar is equal to minus 1, so in the case where x bar is equal to minus 1, we have the following. I of x bar is equal to 1 and 2. Okay? So similarly, we can obtain the formula for computing this active index set I for any x bar in the domain of the function. Now I'm going to continue with the main formula for this lecture. Under the assumption that each function fi is continuous at x bar, we obtain a very nice formula in order to represent the subdifferential of the function f in terms of the function fi for I from 1 to m. Now, if each fi for I from 1 to m is continuous at x bar, then we have the following. The subdifferential of the function f at x bar can be represented as the convex Hall of the union of the subdifferential of fi at x bar, where I runs in the active index set at x bar. Okay. So in the following part of the lecture, I'm gonna give some examples and also give the detailed proof of this formula. Okay. In order to understand the formula, let's look at this example again. In this example, at the point x bar equals 1, we're gonna apply this formula in order to obtain the formula for the subdifferential of the function at 1. Okay. Let x bar be 1. Okay. Now, as you can see here, each of the functions here is continuous, so we are able to apply this formula. In this situation, we see the following. Then, as we computed earlier, I of x bar is equal to 2, 3. Then, for the first function, f2 of x equals 1. We see that this function is differentiable, so the subdifferential of the function f2 at x bar is just the derivative of the function at this point, so it contains a singleton that is 0. Okay. Similarly, for the third function, f3 of x equals x, then the function is also differentiable. So the subdifferential of f3 at the point x bar in this situation is the same as the derivative of the function, so it contains a singleton that is 1. Okay. Because of this formula, we see the following. Then subdifferential of the function f at x bar is equals to the convex Hall of the union of the subdifferential of fi x bar, where I runs in the active index set. That means it's the convex Hall of the union of the subdifferential of f2 at x bar and the subdifferential of f3 at x bar. So this is just the convex Hall of the set that contains 1 and 1. I'm sorry, contains 0 and 1 in R. So this is just the closed interval 0, 1. Okay. So we can also see that from this formula. This is the function f, and then we can see that the slopes of the subtangent lines of the function at 1 range from 0 to 1. So our obtained formula here is consistent with what we know about subdifferentials. Now I'm going to present another example in order to understand the subdifferential maximum rule. In this example, we are going to consider the absolute value function. As we know, the absolute value function can be represented as the max of two functions. The first function is f1 of x equals minus x, and the second function is f2 of x equals x. Okay, so consider the following functions: f1 of x equals minus x, and f2 of x equals x. Over here, x is in R. Then the function f of x defined by the maximum of f1 of x and f2 of x is the absolute value function. Okay. Now, at first we're going to look at the point x bar equals 0. In this situation, we can easily see that f1 of x bar is equal to 0 and f2 of x bar is also 0. Therefore, f of x bar is 0 as well. From the definition of the active index set at x bar, we see that I x bar equals 1, 2, because the maximum is attained at both of the functions. So by this subdifferential rule, in order to compute the subdifferential of the function at x bar, we compute the subdifferential of f1 at x bar, the subdifferential of f2 at x bar, take the union, and then compute the convex Hall. Okay. Now, in this situation, the subdifferential of f1 at x bar is the derivative of the function at this point. So this is the singleton set minus 1. Okay. And similarly, the subdifferential of f2 at x bar is 1. Then the subdifferential of the function f at x bar is equal to the convex Hall of the union of the subdifferential of the first function at x bar and the subdifferential of the second function at x bar. Okay, so this is just the convex Hall of the set consisting of minus 1 and 1 in R. So it is just the closed interval minus 1, 1. And this result is consistent with what we know about the subdifferential of the absolute value function at 0. Okay. Similarly, we can easily compute the subdifferential of the absolute value function at any point x bar in the domain of the function using the subdifferential maximum rule. Now, I'm going to get back to proving this formula. In the first proposition, we're going to show that this inclusion is always satisfied without assuming the continuity of the function fi. Okay, so let me go ahead and present the proposition. We always have the convex Hall of the union of the subdifferential of fi at x bar, where I runs in the active index set at x bar, is a subset of the subdifferential of f at x bar for any x bar in the domain of the function f. Okay. Again, in this proposition, we do not assume the continuity of fi for I from 1 to n. So the proof of this formula of this inclusion is very simple. So I'm going to go ahead and give the proof. Observe that the subdifferential of f at x bar is a convex set. So this is a very important property of the subdifferential of convex functions presented earlier. So now in order to show that this inclusion is satisfied, we're going to show that for each I in this active index set, the subdifferential of fi at x bar is a subdifferential of f at x bar. So fix any I in ix bar and v in the subdifferential of fi at x bar. Then by the definition of the subdifferential, we have the following: the inner product of v and x minus x bar is less than or equal to fi of x minus fi of x bar for all x in Rn. Okay. Since I is in the set ix bar, by the definition, fi of x bar is equal to f of x bar. Okay. Moreover, because f of x is defined to be the max of fi of x for I runs from 1 to m, obviously fi of x is less than or equal to f of x for all x in Rn. It follows that the inner product of v and x minus x bar is less than or equal to fi of x minus fi of x bar. This is what we have over here. And this is less than or equal to f of x minus f of x bar. This is true again because this is equal, and also fi of x is less than or equal to f of x. And this is true for all x in Rn. Therefore, the subdifferential of fi at x bar is a subset of the subdifferential of f at x bar. Now, as I runs arbitrarily in this set, we see the following. The union of the subdifferential of fi x bar, where I runs in I of x bar, is a subset of the subdifferential of f at x bar. And as I mentioned earlier, this set is convex. So the convex Hall of this set is the smallest convex set containing the set. So from here, we obviously obtain this inclusion. Therefore, the proof of the proposition is complete. Let me continue with a very important lemma used in order to obtain the formula for the subdifferential of the maximum function. This lemma contains two parts. In the first part, we have the following. For a convex set omega in Rn, if the interior of omega is non-empty, then the relative interior of omega is equal to the interior of omega. And if x bar is a point in the interior of the set omega, then the normal cone to omega at x bar reduces to 0. Okay. This fact is rather simple, so I'm going to explain from a figure. Now in this figure, this is a convex set omega, and this is x bar. Now in this situation, we can easily see that the normal cone to the set omega at x bar is just the singleton 0, as x bar belongs to the interior of the set omega. At the same time, in this situation, we can easily see that the alpha factor of omega is R2 because the interior of omega is non-empty, and therefore by the definition the interior of omega is the same as the relative interior of omega. The proof for the general case is very similar. Now I'm going to focus on the second part of the lemma, showing that if f is a convex function that is continuous at a point, then that point belongs to the interior of the domain of the function, and also we have this implication. Okay. Now suppose that f is continuous at x bar in the domain of the function f, then we have the following by the definition of the continuity. For epsilon equals 1, there exists delta greater than 0 such that the absolute value of f of x minus f of x bar is less than 1 for all x in the ball with center at x bar and radius delta. So from here, we because f of x bar is a real number, so f of x has to be a real number for whatever x in this ball. That means the ball with center at x bar and radius delta is a subset of the domain of the function f, and therefore x bar belongs to the interior of the domain of the function. Okay, so from here we see that then the ball with center at x bar and radius delta is a subset of the domain of the function f, and so x bar belongs to the interior of the domain of the function f. Now I'm going to prove this implication. So we're going to fix any element v minus lambda in this normal cone and show that lambda is greater than or equal to 0 and v belongs to lambda times the subdifferential of the function f at x bar. Okay. For any element v minus lambda in this normal cone, by the definition we have the following. The inner product of v and x minus x bar plus minus lambda times gamma minus f of x bar is less than or equal to 0 whenever x gamma is in the epigraph of the function f. That means gamma is greater than or equal to f of x. This follows directly from the definition of the normal cone in Rn plus 1. Okay. Now, in the first part, we're going to show that lambda is greater than or equal to 0. Because this is true for whatever x gamma in the epigraph of the function f, we're going to apply this for a particular element of the epigraph. So let x be x bar and let gamma be f of x bar plus a positive number, for example 1. Then we can easily see that this x gamma belongs to the epigraph of the function f. And therefore, when we plug in here, we have the following. The inner product of v and x in this situation is x bar, so x bar minus x bar plus minus lambda times gamma over here is f of x bar plus 1, and then we subtract f of x bar, and this is less than or equal to 0. So here it is 0, this is 1. From here we have that minus lambda times 1 is less than or equal to 0, and therefore lambda is greater than or equal to 0. Now I'm going to prove the second conclusion of the implication. That means v belongs to lambda times the subdifferential of the function f at x bar. Let's consider two cases because lambda is greater than or equal to 0. The first case we consider is lambda strictly greater than 0. Now in this situation, because v minus lambda belongs to this normal cone, and the normal cone is a cone, so whenever we divide this element by a positive number, then we still have an element of this normal cone. So then we have the following. V minus lambda times 1 over lambda. This is a positive number. So this element is still in the normal cone to the epigraph of the function at x bar f of x bar. Okay, it also means that v over lambda minus 1 belongs to this normal cone. And from here, by the geometric characterization of subdifferential, this element v over lambda belongs to the subdifferential of f at x bar, and we talked about this in an earlier lecture. So from here we can easily see that v belongs to lambda times subdifferential of the function f at x bar. So the proof is complete for the case where lambda is strictly greater than 0. Now let's consider the case where lambda is equal to 0. So from this inequality, that is true for whatever x gamma in the epigraph of the function, we can apply this for any x in the domain of the function, and gamma is equal to f of x. Now for any x in the domain of the function f, and gamma is equal to f of x, it is obvious that x gamma belongs to the epigraph of the function. And from here, with lambda equals 0, we have the following. The inner product of v and x minus x bar is always less than or equal to 0. Now, because this is true whenever x is in the domain of the function f, we see that we see the following. We see that v belongs to the normal cone to the domain of the function f at x bar. And before, we already proved that x bar is in the interior of the domain of the function. So in this situation, this normal cone reduces to 0. Now, from this result, we can see that v is also equals to lambda times the subdifferential of f at x bar. because v here is equal to 0 and lambda here is also equal to 0. Note that because x bar is in the interior of the domain of the function, we can also see that this subdifferential is not always non-empty. So the formula is also true in this case. Therefore, we always have that v belongs to lambda times the subdifferential of the function f at x bar.